So good afternoon or good morning for everyone. If you are one of the brave people that stayed until the end of the course, today I'm going to talk about the idea of the proof of modernization of morphisms. And this is probably the talk that I was looking most forward to. So if you stick with me up until here, at least this one I had pleasure preparing it. So hopefully it's going to be something that's understandable too. So let's do it. So I want to talk about now the idea of the proof of modernization of morphisms. And up until now, what we have done was to make considerations on the target and to talk about applications of the result. So today, my idea is to talk mainly about the source of the morphism. But before that, I want to restate the result in a little bit different way. And I want to start by motivating why. So in the theorem that we had a hypothesis on phi. Right. So I started with a question: why phi of m to n proper? So why are we asking phi to be proper? And the reason we can see with a simple example. So suppose that we have phi from a disconnected, so it's going to be a countable disconnected set here. Let me take R, just R, and I'm going to index it with I in the natural numbers. And this is going to arrive in R2. R2 is the target, is Rn. So it's not going to be a proper morphism. And in here, let's call it phi, the restriction to each one of these Ri's, which is simply a function from R to R2. And which is given by say u, which is sent to u square u 2 to the power I plus 1. So if we recall the idea that we had when we talked about the target, we're going to see that this morphism, like once we fix the Ri, oops, not R to the power I, just Ri. What is going on here is that we're sending here to a cusp given by the equation x to I plus 1 minus y squared equals to 0. So for each y, we have a different cusp. And we noted that in order to mononormalize this morphism, we must, in order to mononormalize by I, we need to resolve this curve. And resolution of this curve means making at least I plus 2 blowings up. So when y was equal to 1, that was the cusp. It was x3 minus y squared. Was the case that we treated in details. So in general, if we have a general I, we need to perform I plus 2 blowings up in the target, all of which are going to be in the same R2 and are going to project into the same in the same point, the 0, 0, which project into the origin of R2. So this is showing that indeed you're not going to be able to mononormalize this morphism here, because if you consider all of them, you would have to have an infinite number of blowings up of the point, which like you have to project to blow up the origin and then blow up again a point and then blow up again a point, an infinite number of times. So you're not going to be able to finish this process in the target. At least if you stay here with the target, you would have to use countable many copies of the target, and then this is not going to be a locally finite covering. So you're going to have problems of this form. So really the reason for choosing proper is that to a certain extent is to avoid that you have too many relations in the target. You have a countable number of relations. You want to have finite ones. So keeping things proper means that you can your fiber is going to be compact, and therefore any relation that you have, you can just find a finite number of relations in the target, and this you can resolve. Okay. So we could restate the theorem in the following form, in a currently weaker form, but which actually implies the other and doesn't need proper. So let phi of MD to NE be a Q-morphism, quasianalytic morphism. Let us fix a point A in M, and B is the image of A. Then what we can do is that there exists a neighborhood V of A, well, not only one neighborhood, and W of P, and a finite number of commutative diagrams it's going to be a local version of the resolution of singularities locally at A and B. Right? Of the local d lambda. And here we're going to go to V, or the restriction of V to V. Like this. We have our original morphisms phi restricted to V. We're going to write it. WE. Tau lambda. Here we're going to have T lambda. So now only finite, we don't need cover by countable many of them, such that, as usual, sigma lambda and tau lambda, so we note it as 1, are finite compositions of local blowings up and power substitutions. True, phi lambda, tau lambda are semi-proper coverings. And 3, phi lambda is monomial. So this recalls us what is the theorem that we're trying to prove today, or that we're going to understand the idea of the proof. And it is the beginning, and note that we are going to restrict ourselves to some neighborhood. So in here, we could have done that, right? If we just restrict to a neighbor for each one of the points, then the relation is just a cusp, so we can do it. This, we won't need any condition for the morphism to be proper. It's just when we want a covering of the entire varieties here and we want it to be countable, then it's necessary to add some hypothesis either on phi or to do some little bit of topology. But essentially the technical result that we need to prove is this one. Okay, this local version of the modernization. So let me start by talking about its proof. Okay, so first of all, this result here, we see that then, since we're going to restrict ourselves to some V in the source and some W in the target, we may suppose as well that the target is Rn. We may suppose that the target N is equal to Rn. And this allows us to start the process already with some fixed coordinate system, and therefore write the morphism in a special way. Okay, so this here, consider phi given by the first entries that we have here, Fn. So we are now in Rn, so we can just write phi in terms of we take one of the coordinate systems and we find phi in terms of this coordinate systems in the target. And we will monomalize phi one entry at a time. What does it mean? It means that we're going to consider this Morpheus here, which I'm going to call it phi k, given by the first k entries. And we're going to prove by induction on k that we can monopolize the next one. Okay, in time, we will assume, we will argue by induction. pk monomial starting with 0. 0 is just the constant function, implies we may modify, implies what, you know, we may modify the source and target so that pk plus 1, which I recall that is just pk, and the last entry is monomial. So that's the idea. One thing that we can suppose in this structure here, not remark, but remark. We may suppose that the Morpheus phi k is dominant. That is, the generic rank of it, the generic rank is equal to k. This you can always do because we may as well suppose that if there are some zeros, we may just take away the 0 entries. We don't need to consider it, right? And just consider again and continue the induction, but with all those 0 entries. It becomes even simpler in some sense. So we may as well suppose that all of the entries of the phi k are different from 0, and that phi k is going to be monomial. Okay, so this is kind of the idea. And then we're going to follow 3 steps. Now I'm going to come back to these steps because the first one, I don't want to state it just yet. Okay, I want to keep it for now open, what is going to be the first one. And once we are a little bit more advanced and know what we're aiming for, I'm going to come back for it. It's going to be it's going to be easier than the second step, and it's going to actually be auxiliary for the second step. The second step, we can already explain what we want to do. Oops, no. So I'm going to call 1b. And I'm calling 1 because 1 means that it's only on the source, the things that we're going to modify, or we're going to concentrate ourselves in the source, which is going to be transforming pk plus 1 into a Q function, a quasianalytic function, which satisfies a certain normal form, v plus an m, such that the first thing is that if we consider this Morpheus here without the G, without this G, is monomial. This Morpheus is monomial. And the second part is that and I'm going to write and then I'm explain what does this mean. Oops. If I take the wedge of dg with d phi1 up until d phi k, I obtain that this is 0. Okay. So the reasoning for doing this, so condition 2, implies that the generic rank of pk with just the last entry in G is k. So we have k plus 1 entries, and we know that this phi k with G is of rank k, so we can expect a relation here. We can expect that there's going to be a relation in the target, and that we're going to have to deal with it by modifying the target. Okay, so I'm going to keep this structure up like this.
Sorry, Andre. So M,
yes.
M is supposed to be what afterwards?
M is a function such that K and M is monomial, is a monomial.
Okay. So it's simply a Q function.
Oh, right, yeah.
Right, it's not a monomial, whatever. Okay.
Yeah, GM Q function. Well, in the end, it's going to be monomial, but a special monomial, not any monomial.
Yes, at the end, yeah.
Or I'm going to actually write the normal forms that we have in the next remark. I just want to finish the 3 steps, and then I'm going to talk a little bit more. Just to give the definition, we call, in this case, once we get this normal form, we call this phi k plus 1 here, which is phi k G plus M, a premonomial morphism. And the last step, as we might imagine, is to transform premonomial morphism into a monomial morphism. Transforming to G equals 0. Okay, so a couple of comments about this in a more serious tone. So in order to also address what was just asked, right? No, before it. So if we are able to do all of this, then we're good, because if we were able to transform into G equals 0, then we're going to obtain that actually the phi k plus 1 is a monomial morphism, because the phi k plus there's many k's here, but the morphism phi k plus 1, which is in here, is going to be monomial, because the last entry is just going to be equal to this m, and we know that phi k m is monomial. So then we won, and we follow up by induction. We continue the induction process. So this is the essential idea. So let's comment a little bit more about what premonomial is. So the first thing, what is this M, right? So M, or let me write like this, might be no, like belongs to, it's either 0, no, it's not right, like not set theory class, because this is not, oh no. Oh, okay, this problem. Oh, well. M is equal to either 0 or u to some power alpha or some u to the power beta v plus phi. It's one of these forms, right? That we can assume. The second thing that I wanted to say is an example of premonomial. And the cusp is a good example. So if we just take phi from R to R2, U that goes to U square or U third, U square, U third is premonomial. Okay, so in this case, I will call phi 1 equals to U square, phi 2 equals to U third. And in this case, the phi 2 is just equal to G plus M, where G is equal to U3 and M is equal to 0. So in particular, this is the part of the proof where we really, so we made an assumption here that we said that we may suppose, apart from taking away zeros, that the morphism is dominant. But we do treat the non-dominant case, and we treat it in an explicit way, because when we assume that something is premonomial, we are not assuming that it is dominant. It might have, if the M is equal to 0, then the generic rank is going to be K, right? So it's not going to be K plus 1. We are not dominant in this case. And therefore, we are dealing with relations in the target. And this kind of captures the heuristic of why we want to have this division here. The G will correspond to the relations with the privates and degrees of the morphism. So we expect, as a second entry here, that we will need to modify the target. And that's actually what we do. In the part 2, we'll modify the target, and we basically modify the source by induction. So we need to modify the source because we need to blow up something in the target, and then we use results that by induction says that, okay, there's a commutative diagram, but we're really just focusing on the target. And whenever I write the 1 in this part here, once I want this normal form, this M appearing here, this M does not have, it's not going to be having relations with the previous entries of the Morpheus. So unless it's 0. So this is the part where we're going to modify the source. So the part 1 here corresponds because here we're going to really fix on the source, and we modify the target by induction. So we're going to make modifications of the target, and then of course we need to apply maybe this 3 steps for a Morpheus with less entries, and then it's going to appear some modification of the target. But we're going to use it almost as a black box. Okay, and the idea today is to concentrate on this part B here for a while, and then we're going to see what is going to appear in A in a moment. But okay, this is the class, this step. So on the source. We want to start with some sort of question here to lead a little bit for the first observation that we're going to have, which is kind of funny question to ask at this point, but why is this not trivial, right? Why is this not trivial? Why is the problem? And by this, there is an idea behind that that I think that we might think, or we might consider in an easy way, which is, okay, now we are in a local case, so why don't we consider the ideal I given by the product of all of these phi i's? And if we want to be fancy and even order this monomial, because why not, we can even take the difference between them. Something like this. And now we apply local resolution of singularity, and we apply local resolution of singularities so that we may assume that I is actually equal to u to some power, which one did I use? Not gamma. U to some power gamma. So this is simultaneous resolution of singularities, sometimes this is called, right? So in this case, then, what happens is that you're going to have each one of the entries is going to be given by some u to the power alpha 1, and I'm going to write here c u v w. Cn is going to be on u to the power alpha n. Cn u v w, and we know that these c's are units. Because each one of them have to divide this u gamma, and then therefore they have to be a u to some power times something, or a unit or something. So if we do this, assuming that none of these phi's are 0, right? Take away the phi's which are 0, we can bring it to this form. So now, why is this not enough to finish, right? The point is that we still need to absorb these units into the monomial, and we cannot do this for all of them at the same time. But in general, we can't absorb all units. And the easier way to see this is just by an example, in my opinion. It's not the easiest for everyone. So let's consider the Morpheus here from C3 to C3, or to R3 to R3, it doesn't matter. Let's say that we take x1, which is this phi 1, is equal to u to the power 3. The second entry is going to be u to the power 3, 1 plus u v1 plus v2 squared. Let's say that x3 is equal to 3, and I noted here u5, because why not? v2 plus 1. Now, let me just make it even simple. Oh no. Again, I cannot do those. Let me just keep like 65. So here the point is that, okay, every one of the entries are monomial, but we do not have a monomial morphism yet. And we can see this because the monomial morphism is going to have something more rigid than this. So this is a unit we cannot all absorb. If we try to make a change of coordinates here in u and absorb all of this unit into u, so we're going to make a change of coordinates of the form u tilde equals u times the third root of this function here. Then we're going to appear a unit in the other part here. So we're not going to be able to get rid of this unit. And another way to see this is that if we make a change of coordinates in the target, we consider x tilde 2 equals to x2 minus x1, then this x tilde 2 is going to be equal to u4 v1 plus u3 v2 squared, which is not in monomial form. So there's something more subtle about, more rigid about in a monomial.
Sorry, Andre. So I don't understand your last point. I mean, why would you want x2 minus x1 to be a monomial?
No, it's just I'm trying to make a because I'm going to try to make a point with the other part, but you're right. Why would I could change coordinates and then don't obtain a monomial morphism again? It's not clear yet.
Okay.
It's a good point. But the first part is just the first point is clear that I cannot absorb everything.
Yeah, that one is clear. Yeah, totally clear. Yeah.
Yeah, no, I'm anticipating the point that I'm going to make next. Okay, so what's the point that I'm going to make next? Is that things are more rigid. And for that, I wanted to recall, but in a like weaker form, monomial morphism. Without simple normal crossings. So just the definition of what monomial morphism is, but without carrying out the simple normal crosses, which is a technical point. It's very important for the proof. But for today, just let's focus on the heuristic. It's not going to appear the technical details with the normal crossings. So let's just recall phi of n to n is monomial at A if there exist coordinate systems u vw at A, x, y, z at phi of A, which you will normally denote by B, such that xi is equal to u to the power alpha I, yj is equal to u to the power bj plus xij, zk is equal to vk, and finally, or zk equals to 0. So here was for I equals to 1 up until p, j from 1 to q, k from q plus 1 up until s, and k here from s plus 1 up until what we call s prime. I should have written this completely so that we feel happy about it. This is up to r, v1 goes to vs, w1 goes to wt, and then x1 goes up until xp, y1 goes up until yk, and then we had k plus 1 up until s prime. That was the way that we were given. And we had two conditions: the set of alphas, are Q, not quasi-analytic, just Q, linearly independent, form a vector space of dimension P, and beta J is Q, linearly dependent with the alpha 1, alpha P. These were the conditions. So we had this nice looking normal form and this extra condition. So we talked a lot about what happened in this in the target. But now I want to talk about, once we have these normal forms, a property that is going to be intrinsic here about this morphism, about a morphism with this form, is that the level set is going to be very, very rigid. So this is the next point. So following this definition, I want to talk about the level set. The level set of a monomial morphism is very rigid. So maybe let's start with an example, a couple of examples, and then I'm going to complete the definition that I want to put here. So let's say that we want to consider, I was going to do it, but I think that it's a good thing to do this. Let's say that we consider Morpheus phi from C3 D to C2. Why am I taking C3? I can take R, because I copied from the paper. R3 to R2 E. And in the first example, let's take D being U1, U2 equals 0, and E being X1 equals 0. And then we have a normal form here, X1 or X, because there's only one X. It's going to be equal to U1, alpha 1, U2, alpha 2. And then the next coordinate Z is going to just be equal to the Z, to the last coordinate. There's not up here. So this is our morphism from R3 to R2. Okay. So the level sets, in order to compute the level sets of this morphism, I'm going to search for the vector field. Right, the level set is going to give us a foliation. In this case, I have something from dimension 3 to 2. So the level set.
Can you hear me?
I can hear you, yes.
Oh, yeah, I've been struggling, but not for very long. Can you insist a little bit on the, maybe you did already, but on the difference between the definition of monomial morphism without essency and the original definition that you gave us?
The definition, this one?
Yeah, this one and the previous definition, which I...
Oh, it's the same. I'm just not putting the condition on the simple normal crossings. So okay. the conditions was that U was the normal crossing divisor of M, and X and Y gave us the normal crossing divisor over N.
Mm-hmm.
Yeah, that's it. I could have added also, I just didn't want to focus on it.
So, okay, so you don't have divisors in this case? But...
No, it's true, yes. Yeah, it's true that, and here I didn't need to put a divisor in some sense if I want to follow here. It's true. Okay. Is that why you are, yeah. Good point.
Yeah, first, is my microphone making a terrible sound? Because some people look like it's no. Is it okay?
I mean, no, it's okay. It's okay. No,
Yeah, I think I always have trouble understanding the role that the devices play in these theorems. But yeah, because you're always trying to
I'm actually going to insist on it.
compatible way with a set of devices because you're building resolution. So
because and in the end, what we want to use, what's going to appear is the derivations which are tangent to the divisor too, just as we did in the local resolution case. So that the devices are going to appear right away here. So that's why I feel like I'm going to insist on it now.
okay, thanks.
So, okay, so the level sets of this morphism is going to be given by curves or points, right? And it's going to generate for us a foliation. So a foliation will be able to see it via a vector field in this case. So we consider the vector field, we consider a vector field. X, which I'm also going to assume to be tangent to the divisor, so it's going to be of the form A1, E1, G1. Why did I take B? A2, U2, the U2, and then the B in the last one, plus B dV, right? And in order to find that it's going to generate the level curves, what we need is that it has to be tangent with each one of the functions, such that X of U1 alpha 1, U2 alpha 2, this must be equivalent to 0, and so does X of V must be equivalent to 0. So X of V is just B. So we are just saying that the coefficient B is constant equal to 0. And this other one is going to give us, since it's going to be, there's this U1, it's going to give us U alpha 1, U alpha 2, which multiplies alpha 1, A1, plus alpha 2, A2, that we also want to be equivalent to 0. So this gives us relations on the coefficients A1 and A2 that we must satisfy. So from this we take that X must be equal to a function A, which multiply the vector field, because there's a relation between A1 and A2, so there's going to be a common function A here, which multiply alpha 2 U1 the U1 minus alpha 1 U2 the U2. This is the term here that's going to make this part here become 0, right? And then there's a common factor. So this term here is the generator of the foliation, of the level sets. Which is a linear vector field. In a similar way, if I take another example, so this was the point. I started with this monomial morphism. I realized that the level curves are generated by a vector field which is linear. And if I try something a little bit more involved as an example, and consider now.
Sorry to interrupt again. So you consider the level sets, the collection of level sets as the leaves of a foliation of a
right.
field. Yeah, okay.
What is the level set, right? I'm considering the terms phi equals to constant.
Yes, so you see that as a foliation. This.
And I'm seeing that as a foliation. So this is giving me some partition of the entire set.
Right.
So what is being claimed is that if we have this form U1 alpha 1 U2 alpha 2, then the vector field X that we're doing here, it's going to look like in the U1 U2 is going to look like a saddle. So you're going to have like this. The leaves. And if we change to any other level here given by some other v equals to 1, for example, is still this kind of saddle vector field given by this one. So it's a family of this, not a family because there's no changing parameters. It's a three-dimensional vector field, which is the v entry does not make a difference. In every point, it's just giving us corners. So it's going to be tangent to v. It's tangent to the level sets of v equals constant, and it's going to be also tangent to the level sets of u1, a1, u2, a2 equals constant.
Yeah, okay.
So now u2, u3 equals 0, and e x1, x2 equals 0. So both of them. And let's take x1 equals to u alpha 1, u3 alpha 3, and x2 given by u1, let's say beta 1, u2 beta 2, u3 beta 3. Okay. So if we wanted to play the same game, we want to find out the level sets. So we are interested in knowing which are the level sets of phi equals constant. We're going to search the vector field that makes both of this, the generator, right? Just as we did here, that annihilates both of these entries. So we search a vector field, we search x equals to the sum of AI, UI, GUI, so tangent to the exceptional divisor, such that x1 must be constant equals to 0, and x2 must be constant equals to 0. This is going to give us the level set of the vector field. Then we'll generate a line foliation, which will coincide with the level sets. It's going to be tangent along both of them. Both of them are first integrals of them. So the foliation itself is going to be tangent to both of these functions. In this case, just as before, like what was appearing here was we didn't have the v did not make an appearance, and the alpha 1, alpha 2 was such that the determinant here was, if we think about there was the alpha 1, alpha 2 here, there was the vector space generated by alpha 1, alpha 2, and what we took here was alpha 2 minus alpha 1, so we took the orthogonal space. Because once we take the orthogonal space and you multiply it to the inner product with alpha 1, alpha 2, this is going to be 0. So in here, to generate this vector field, we can do the same trick. We consider gamma equals to this alpha beta, right? In dimension 3, we can just take the vector product, and x given by the entries of this gamma, ui, gui, generate the levels, the foliation, the level sets of phi equals to constant. Now, this is going to be the vector field that is going to give us, that is going to describe all of the level sets of the foliation. Okay, so this can be a little bit more involved because it's a three-dimensional vector field, but you might have a situation that some of them, you do some drawing, you could have a situation of something radial here, and in the other ones you're doing something like that. For example, as an example, what could have been depending on the choice of alpha and beta that we take here. But one thing that is important once again is that this is again linear, so this is very rigid. So what is the object that we are going to consider in both of these cases? We want to consider this foliation, these level sets, which we're going to describe as a foliation. So we're going to describe it with a model of, or a sheaf of models of derivations. Okay. So the level set phi equals constant gives rise to a foliation, and we describe this foliation via its vector fields. Yeah. one of the definitions in algebraic geometry. So we consider the K sheaf of modules, which we're going to call gamma phi, which is going to be contained in the sheaf of derivations tangent to the exceptional divisor, such that for every n, a and n, we give them by the stalk of what is going to be. So phi at a, this is going to be the vector fields in dE in the stalk A. So what we want is that it is going to be tangent to every one of the entries of the morphism. So one way to say this is that x of f composed with phi is constant equals to 0 for all f in the local ring of the image. Right? So if we are in this situation, we're just pulling back x and z, or we're pulling back x1 and x2, but we could have pulled back any other function. It's still going to be 0. So this is going to be the sheaf that is going to describe this level set. Of log derivations tangent to phi. So just to say the point that I anticipated a bit too early in this example was that once we make this change of coordinates, we're going to remark that at least the first two entries here, the level set is not going to be linear. It's going to have a more delicate singularity here. So the vector field is not going to be linear. That's just the point. So that was, I anticipated this was the second point that I wanted to make. So this is not going to be monomial because the level sets are not going to be good. And when I'm saying that the level sets are strict, so we talked about these two examples where we saw that the level sets were given by this vector field, which is linear, but this is actually a more general result. Now I just give it to you. The following one. Lemma. Suppose that phi of MD to NE is monomial. Then first information, this sheaf of models is a finite type. It is not strange because locally, right, after change of coordinates, the morphism is algebraic. It looks like an algebraic morphism, and therefore the sheaf almost like an algebraic sheaf and not a quasianalytic sheaf. So you can expect that it's going to be of finite type, not only privileged. Actually, finite type here is important because it's not a priori clear why the sheaf for any abstract morphism that we define here would be privileged. But actually, it's much more than just privilege, it's a finite type. Okay, in the case that it's a monomial morphism. And the sheaf at A is generated by vector fields of this form, yj equals to the sum k equals to 1 to r, gamma jk, uk duk, where j equals to 1 over r minus p. I'm going to explain why this notation here in a second. And zl is just going to be equal to dwl. W equals to 1 to t. So finally, the W variable appears. The W variable, which we sometimes call phi free, is the one where we have derivations in this sheaf, which are regular, which are not singular, right? These ones are singular. They are u times the derivation. They have to be tangent to the exceptional divisors. These ones are not singular. If you derive WL, you get equals to 1. That's what it means. And we can even say a little bit more so that we're a little bit more precise about this, where the collection of all of these gammas R minus B forms a basis of the orthogonal complement of alpha 1 alpha P. So just as before, in this example here, you had alpha, well, the two were alpha, right? So you have the vector space generated by alpha and beta, and then gamma was an orthogonal one. So this is a more general phenomena. You can always take this sheaf as locally generated by vector fields of this form, linear in the U variables and regular in the W variables. So this means that the level sets are really rigid, are very special foliations. Okay, so this kind of explains why we are going to need something. In some sense, we need to. So let me write. We're going to need to not only deal with the normal form of phi, but also with the level sets of phi. So there is considerations about the derivatives here that are changing. Considerations that go in the direction of foliation theory. Although we don't have transcendental behavior because everything has a first integral. Something intermediate between them. So the problem of modernization
Sorry, André?
Yes.
So you gave only one index for the gamma I between the brackets. So I take it's gamma 1k to gamma r minus 1k, which form a basis. And so does it mean also that we can pick them independent of k?
Yeah, they don't depend. Sorry. So maybe I should have been clear. When I write gamma 1, I mean the vector given by gamma 1, 1, gamma 1, r.
Okay, each gamma.
Sorry, I should have been precise. This J is fixed, and the K is varying, and then I'm taking the multi-index.
Okay, sorry.
Right. No, but this shows that you're following, so good. There's many indexes to be precise. Okay, so it demand. Let me write this in a better way. Transformations in the source such that, well, we want to some extent resolve the level set and at the same time obtain monomial normal forms. Of course, the second one is the one that we're really after. But the first one is going to play a role in the proof. It's going to play an important role in what follows. So I wanted to put up it in a special way that we also want this level sets to be nice. And this is going to play a role on how we define invariant and etc. that we're going to work with. Okay. And now this, so this was the first, and now the second one that I wanted to make is, let's now consider the monomial morphism, a pre-monomial morphism. So from the beginning, right? So we had phi k plus 1 was equal to this phi k. And then we wrote g plus m. Where g was a relation. So d phi 1, d phi k, dg is equal to 0. And if we disconsider the relation g, then this is monomial. And the first thing I want to remark is that now if we have a vector field in this sheaf, right, and we apply to g, then we're going to get 0. So if x belongs to this sheaf, let me not be precise about the point. We don't have to germify. Then when we apply to g, we're going to get 0. And this is coming from this property here. It means that if we have something which is going to be like it's an exercise to do it, but the heuristic is that a g is related, right? There is a relation with this phi1 phi k. So although we don't see it necessarily as a function in the target, the relation is already captured by the level sets. We're not going to define, like the level sets are not going to change if we add the Morpheus phi kg. They're going to be exactly the same. We're not going to change them. We're not going to have something smaller there. So this is the first point here. And because of this, we can now see that if we apply these derivations that we have here to the pre-monomial morphism, to the last entry of the pre-monomial morphism, then we're going to be able to find an intrinsic way to see this monomial morphism, that it is a pre-monomial morphism. So let me be more precise about this. So consider the ideal J, which is given by the derivation of phi k plus 1 for all and here with a k. Okay. We consider this J here. And let us compute it in the case of a pre-monomial morphism, right? So there's basically three cases. If m is equal to 0, then nothing to do. J has to be equal to 0 because every derivation that we take here is going to make g equal to 0, and m is 0, so the ideal is 0. Nothing to do there. If m is of the form u to the power alpha, then this alpha was linear independent with the alpha 1 alpha 2p. And therefore, when we take a derivation x of it, right, we are going to be forming a basis of the orthogonal complement. So there's at least one of these derivations which apply to u alpha is non-zero. So as a matter of fact, this g is going to be equal to u alpha. This j, sorry, is going to be equal to u alpha. And third, if m was equal to u beta, v, not v, w plus psi, then the beta was linear dependent with the alphas. So every one of the derivations that are written like here, they're going to make this monomial to be equal to 0. Nevertheless, all of the derivations in w do appear. So once we derive in w here, we obtain just u to the power beta. So we are going to see that j is equal to u beta, which is monomial. And this actually captures, so if we have a premonomial morphism and we consider this ideal j, we obtain something that is either 0 or monomial. And this actually captures a more general statement, which is lemma if j is equal to 0 or j is monomial, then pk plus 1 is premonomial. So what is the point of what I'm trying to present here and construct this lemma? The point is we have this rigidity of the level sets, and now we can use it by applying it to the entry, to the last entry of the morph, the one that we're trying to transform, in order to get a certain ideal, which if this ideal has a good property, if this ideal is monomial, we know that we have finished the step 1b. We know that we are in premonomial form. So now, instead of working with the morphism itself, we're transforming the problem into working with an ideal, the ideal coming from the derivations of this phi, the sheaf of derivations of phi k here. So let me write a little bit better. Okay, right? So once we do this, now we have to deal with an ideal in some sense, right? What we want is to deal with the ideal given by all of these derivations of the last form, which are not going to see the relations G. They're only going to capture what appears afterwards. Doesn't capture things that are going to have to be dealt in the target, but only things that have to be dealt in the source. And our goal would be to make it monomial. That would be a goal for us in that step 1b, right? And if we do that, then we have to consider the target to get G equals 0. So this motivates us to talk about the theorem that I'm going to call 1a. So this is going to correspond to that 1a step. So the first step, the technical step that now makes sense, which is the following. So let phi of md into ne be a Q, but now monomial. This is going to be a hypothesis morphism. So now we assume that the morphism is monomial, and we consider, and let I be a privileged ideal. Then we do the local version, let A in M be equals to P of A, which belongs to N. So there exists neighborhoods V of A and W of B. And a finite number of commutative diagrams just before satisfying all of the properties. One, two, and 3. So the properties about being local points up are substitutions, semi-proper coverings. The phi lambda are monomial. This is not that impressive because in the beginning phi was monomial already. So if that was it, then we could just take sigma and tau as the identity, but the real thing and the pullback of I is monomial. So what we're doing is that we're taking an ideal. We take already a morphism which is monomial, and we take some ideal in it in M. I didn't say where it was. In M. Sorry. Let's put the sheaf in something implicit. That was an ideal sheaf. In M, and we're going to principalize this ideal, and we will preserve the fact that the morphism was monomial. And in here, we are seeing that, that this is the kind of thing that we want. We want to be able to do this because we want to take this kind of ideal J, and we want to be able to principalize it in a way, monomialize it in a way that we keep the morphism phi k that is appearing here, this morphism. We want to keep it monomial, right? So the idea is that we're going to apply it to phi equals to phi k. So we'll go back to the beginning, and I'm going to write that. Theorem 1a with phi equals to phi k. And the ideal, the kind of ideal that we want to derive and we want to monomialize will be related to that ideal J. It's not only going to be that ideal J. We're going to see what exactly we want, but that's the idea. We want to principalize that ideal J so that we are able to finish by saying that it's a pre-monomial morphism. Right? I'm going to take this guy, make it a monomial, use this theorem, make it monomial, guarantee that that therefore we get something that that is pre-monomial. But this J is coming from the derivation of, it doesn't behave as an ideal as we blow up because it's coming, it's not an ideal itself. It was coming, well, we're taking the ideal that generated by derivations of some entries. So this is going to be able, we'll have to do this in a very precise way. But now I will focus more on the first part. And why I'm going to, on this theorem 1a, right? With clearly is important to, which clearly important, which I try to argue so far that it's very important to make the transformation of this J into something monomial and therefore to get us pre-monomial. And the reason why I'm going to focus on this is because the proof is very similar to local resolution of an ideal, right? Which we already did in a lot of details. So my idea now is to take and to present what we need to modify in that proof in order to get the result. Okay. So as a first thing, I want to talk about the morphisms that are going to preserve the normal form of being monomial. Right? So when we did, let's enter in this topic. When we talked about local resolutions, we started by talking about combinatorial blowings up. It was very, very useful for us. And here we're going to try to understand what are the morphisms that we're searching for, right? Combinatorials are going to be some of them, but we might want something more. So morphism preserving transformations. Which preserve So as we did before, a transformation is going to keep everything good, are combinatorial transformations. Monomial. And sigma from M tilde D tilde to MD, a combinatorial going up. Then two things happen, which are good for us. First one is that the composition with sigma, which we can call it phi tilde, is again monomial. So if we make this combinatorial going up, we keep the fact that it's monomial. But there was another property that we talked about when we did local resolution, which we call the key property. And the key property is still true here. That is, if we pull back the sheaf of derivations tangent to phi, this is going to give us exactly the new sheaf of derivations of the composition. We had called this key property. And maybe just to answer a question that came before, why do we keep track so much of the exceptional divisors? Well, one of the reasons is because of this kind of transform, right? If we have combinatorial, if the combinatorial is really dependent on the exceptional divisor, we know that all of the properties that are somehow important for us and going to keep track and control on the objects that we are working with are satisfied. So combinatorial blowing ups are good, but we're not going to be able to prove this theorem only with combinatorial blowing up. So we will have to be much more precise where we use them, and also where we need to use more general transformations, which also have these two properties. So now I want to argue with you that these two properties are what we want to keep, but they are not only satisfied by combinatorial blowing up, and moreover, that in some sense they are independent. They have a big correlation between them, but we might have blowings up that preserve the first and not the second, or we might have blowings up that preserve the second but not the first. So let's do this with examples. I will consider, and here again I'm a little bit, I'm just not taking much importance the exceptional divisors. Let's take empty. And here Z1 equals to V1 and Z2 equals to V2. First, if we take the blowing up sigma, to consider the blowing up here. And I write, this is spanned by the variable W. It's just one vector field, right? It's from R3 to R2, so it's a vector filter. It's a line foliation given by W. So now, if we blow up with center C equals V1 and V2, so this is not combinatorial. Then both properties, this one here is not good, right? Then both properties are satisfied. We can see that if we blow up like this, then this blow up is invariant by the axis given by W. So the pullback of this in particular we're going to have that the blowing up of this phi is still going to be span of the dW, which is now d of sigma phi. And we can see that. So we don't need to blow up only combinatorial. There's more general blowings up that preserve both properties. But if we blow up with center C given by V2W, again, which is not combinatorial, then that's why it was not good. I composed with sigma is monomial. But now this guy is going to have a pole, has poles. And so it's different from the composition. So the second property, so we might make blowings up that preserve the first property, but not the second. And one could present also examples. I won't do it just to move forward, but one can also present examples where the blowing up preserves the second property, but not the first. So from now on, we're going to think combinatorial is not going to be enough, but we want to have a property on the sequence of blowings up, which allows us to have a control. We call this key property because it allows us to have a control on later on some chain of ideals. This is what we are searching here too. But instead of just talking about combinatorial blowings up, we're going to talk about sequences of blowings up which satisfy this property. And this is either going to play a role of a thesis or a hypothesis. In the same way that combinatorial would play a role, right? If we have a sequence of combinatorial blowings up, then something good happens. Or if we have an ideal which is which we call the combinatorial, then there exists a sequence of combinatorial blowings up, right? In the same way, we're going to have statements that says that if an ideal satisfies a certain property, then we're going to be able to find a sequence of blowings up which satisfy this key property. And then statements that say, if such a key property is satisfied, then we can control the invariant that we're going to define in a little bit. Okay, so this is going to still play a key part of the treatment that we're going to have here. It's going to be a property in itself that we want to study. It's kind of the point that I'm trying to make. Okay. So now that we saw this part, let's now build up the calculus of log derivatives in the same way that we did in the local case for ideals. So in the same way as we did before, so let I be a Q privileged ideal sheaf, we consider a chain of ideals where we start by the ideal itself. Now, before it was an index, the exceptional divisor. Now I'm going to put the Morpheus itself. Well, where I need to define it. Ik plus 1 of phi is equal to the previous one plus all of the derivatives applied to the previous one. We consider its closure, which we call this. Ik phi k and n is the delta phi closure. And then we define the invariant that we work with. So given A in M, the invariant at A corresponds to phi of I is the minimum of K in the natural numbers plus infinity, such that ik phi localized at A is equal to I infinity phi localized at A. Right. I'm doing it a bit more faster because this is what we did in the local resolution case. Okay. So maybe now let's compute, given a Morpheus, compute this this sequence here in an explicit way for one example. Let's consider phi of R3 D R2 E D is equal to y. Everything is not great. It's not easy for me to write in this tablet. Equal to 0. And we take, right, do we take again? Yes, this one. We're going to take x1 equals to u1, u2, and x2 equals to u2, u3. And just by doing the vectorial product of the two vectors here, 1, 1, 0 and 0, 1, 1, we can find this guy is spanned by one vector field, which is given by, here I'm going to choose, or maybe let me use the notation, right? It was y, so let me use y. u1, du1 minus u2, du2, u3, du3. And let's take as an ideal, the ideal generated by f, where f is equal to u1, u2 plus u2, u3 plus u2, u3 to the power 4 plus u1, u2 to the power 6. And I want to start by making a couple of observations here about the interaction of this vector field y, each one of the terms that are appearing here, right? So we see that these two terms are actually given by the Morpheus itself. So we have chosen y so that y over x1 and y over x2 is equivalent equals to 0. So if we compute in each one of them here, u1, u2, this is going to be 0. And we compute u2, u3, this is equal to 0. Now, the other two monomials are not like that, right? So if we compute y of u2, u3 to the power 4, then we say we see that the entry in u2 that appears here is going to appear with a -1. So this is going to give us -1. And the entry in the u3 is going to appear with a plus. So here is 4, so it's going to appear plus 4. And then we're going to have the same monomial. We're preserving the monomial by this derivation. So this is just 3 times u2, u3 to the power 4. And if we do the same thing with the last one, then the u1, we're going to apply u1 du1, it's going to be 1. It's going to give us the term that is appearing here. And then we're going to have minus this derivation. So when we apply u2 du2 to this, it's going to have the 6 that is going to go down, but with a sinus of minus. So here's going to appear -6. And then the same monomial, u1 u2 6. So this is going to be equal to -5 u1 u2 to the power 6. Enough. Okay, so now let's use this information to compute this the sequence of ideals, this chain of ideals. And actually, I'm going to be more interested about the invariant itself. So the first information that we have is that if we take y of f, this is going to give us 0 times 0 to the power of 1, is the way to write 0. U1, U2 plus U2, U3. Now it's going to appear 3, which multiplies U2 to the power of 1, U2, U3, 4, plus minus 5, again to the power of 1, U1, U2 to the power 6. And if we apply for the second time, then we're going to have again 0. It was already 0 after all. Plus 3 to the power 2. Because the 3 is a constant. Minus 5 to the power 2. To 6. So we have the 3 entries, and we, of course, I did not write, but we have f. Then there's no 0 to any power, it's just U1, U2 plus U2, U3, 2, U3, 4, plus. And if we make the computation just as with the van der Monde matrix, basically here we're going to have a van der Monde. This is going to have a nice looking determinant. We can invert that matrix, and what we're going to obtain is that we may make combinations of f, yf, and y square of f to generate each one of these monomials and this pair here, the sum, independently. So we conclude that U1, U2 plus U2, U3, U2, U3, 4, and U1, U2, 6 are elements we need to derive twice. So via I phi 2, they are elements of that. And this is going to give us all the information that we need to finish to compute the sequence, because we know that I phi 0 was just equal to this f, and this is contained in the ideal generated by all of these terms separately. U1, U2 plus U2, U3, U2, U4 to the power, U3 to the power 4. I have to keep my concentration. And U1, U2 to the power 6, right? And then we had the first one, which is then going to be given by f y of f. And then the third one, f y of f, which at the one hand, it's going to contain, we just computed it, it contains. So this ideal.
So Andre, we agree that the inclusion symbol is in the wrong direction, right? Or I really don't understand. Okay.
No.
Thanks.
You're right.
Great.
When I'm writing, like when I have to write a lot of things, sometimes I lose concentration. Right? So this one we know that is going to be contained by the previous argument to U2 phi. And on the other hand, we know that this ideal is invariant by the derivations in phi. Right? We have computed them just here. They're invariant. We're keeping them. So they are also something which contains I1 phi, and therefore they also contain I2. So we conclude that the invariant is going to be equal to true, because this one is going to be the I infinity phi. Invariant of phi at 0 is equal to true. We needed two derivations in order to obtain this. Of course. So far I proved that it's smaller or equal to true. So strictly saying, we need to verify that this ideal is not going to be able to give us the three elements, but this is not difficult because it's generated by two elements, and here we have an ideal generated by three. So we do get that it's going to be equal to true. But there's something, and all right, split it one more time. The infinity ideal is this. And there's something which is different from the case of local resolution, which is when we did this closure ideal, we obtained that it was going to be generated, at least formally, by monomials. And this was important because we used a combinatorial resolution of singularities to deal with it. But now, as we can see, it's not anymore generated by monomials. It's going to be generated by power series, where the only information that we have is that the functions that are appearing here, they're going to be they're going to have some nice behavior in terms of the derivations that generate the sheaf of derivations tangent to the morphism. So we're going to make this a little bit more precise later on, but the thing that I wanted to remark right away is that this infinity ideal is it's not even a question of being formally or not. In this case here precisely, it's analytic, even algebraic. We do see that it's not given by monomials. We cannot solve it, we cannot resolve it, sorry, by combinatorial blowings up. We will need something more general. Okay.
André?
Yes.
Sorry, I2 is generated by F, Y of F, and Y2 of F, maybe, no?
Yes, sorry about this, you're right.
Okay.
Why can I do this? Thank you. Like I'm thinking about the point that I want to make and I don't write stuff. Okay, so now let's try to make the point here. What's the point? Okay. This is the last thing I'm going to take of. I will do two claims. The first one is, in the proof of local resolution of singularities of ideals, step 2 inductive step 2 and step 3 rest the same. By adding to this statement that the Morpheus phi is preserved monomial, right? So this would be the property 3. So my claim is that if we just take that proof that we did and we add to the inductive step statement that, well, we want also to keep some commutative diagram where the morphism is going to be monomial, the proof adapts mutatis mutantis. The same arguments apply. The part that does not adapt is the step 1. So the last part that I want to say is what happens in step 1. So the heuristic of it, no, not the goal of it, I probably write it, consisted. Step 1 consisted in monomializing I phi infinity, this was the first step that we did, right? We considered the entire ideal. We consider the ideal generated by all of the monomials that appeared, which we showed was formally equal to this one. And then we said, okay, we can resolve it. And we make a couple of arguments to say we finished. But we could resolve it. And one of the things which was important was that we could resolve it by combinatorial blowings up. This was something that we used in an important way, because this allowed us to use the key property, which kept control of the invariant. So here we need to do the same thing. So we need to do something similar, but combinatorial blowings up is not going to be enough, because we just seen that this infinity ideal might not be given by monomials. So we actually have to prove a proposition here. So in the notation of theorem 1a, suppose that if we apply all of the derivations, we are still containing the ideal. This is an ideal which satisfies this property, right? It satisfies this property because, if we recall, this is given by the sum of I phi k. So if we apply them, then it's just going to give you the sum of I phi k plus 1. Well, this is going to be containing the sum of all of them. So it satisfies this property. Then there exists the same commutative diagrams satisfying properties 1, 2, 3, 4, that the ideal is going to be monomial, and the key property. Of gamma phi is going to be equal to gamma phi lambda. Right? So this is what is going to replace combinatorial blowings up. So we are going to put ourselves in a situation that in the resolution of singularities of ideals corresponded to a combinatorial ideal. So we knew that we could resolve by combinatorial blowings up. Now we do not know that. It's not a combinatorial ideal anymore. You just seen an example that shows that. But still, we're going to have to prove, that's what we want to prove, that there is going to exist such a resolution of singularities, preserving the monomial morphism, and also keeping track of this key lemma, this key property. Because with such a result, then we can control the invariant. Okay, so I don't have more time, so I want to just make one last point, because this is the last point that I won't present the examples. But this proposition here turns out to be particularly hard in the quasianalytic case, and this is one big difference between the quasianalytic and the analytic case. So maybe the heuristic out of this is that in the analytic case, we made an argument saying that I infinity of phi was equal to a combinatorial ideal formally. And then we said, well, the combinatorial ideal is convergent, so we can resolve. And here something similar is going to happen, but instead of having monomials, we're going to have what we call eigenvectors of the sheaf. And in the analytic case, they converge. But in the quasi-analytic case, they're going to be just power series. They're not going to be just given by monomials. So the same argument does not apply. And this turns out to be a very sensible difference between the two results. So as a matter of fact, in the analytic case, if we come back to the beginning, Did it just lose it? No, it's came back. Okay. If we just come back to the beginning of the text, in the analytic case, we are able to prove 1A separately by using 1A and 2. In this case, we do not need to pass through 1B. In the quasi-analytic, the general quasi-analytic case, we do not know how to prove this theorem 1A without participating in the whole step of the induction. So this is one of the delicate points about the difference between quasi-analytic and analytic. This is a point that makes a big technical difference. In the analytic case, just repeat, we are able to prove theorem, one can prove 1A by just proving part 1A and part 2. In the quasi-analytic, we do not know how to do that. We need to prove also that the morphism can become premonomial. Okay. So since I don't have time, I'm going to stop. But I did with the last point is shows the one difficulty, one of the big differences between analytic and quasi-analytic, and I will stop here. So thanks a lot for participating in the course.
Thank you, Andre. So let's thank Andre since it's his last lecture.
Thank you.
And let me stop the recording.